Here are the syringes. You can see the pointer, right? Hello?
Yes, ma'am. It's
Yeah.
visible.
So here are the syringes. From these tubes, the polymer is coming out. From the needle, the polymer is actually stretched in the form of fibers, and here they are collecting on the, it is called drum collector. Drum collector means there is a drum which is continuously rotating. So yeah, so I will just stop this. So this is basically the final, the nanofibers on the drum. And yeah, so once I basically take it out, it will come up in this form. And this is basically a dressing material of around 60 centimeter length, and if you see the its width, it is around 20 centimeters. So this kind of a long or with a good area, we can design at a single stretch, we can design this kind of wound dressing material. So this is the application. We are working on the wound dressing aspect, but actually this electrospinning technique can be used in various variety of applications like drug delivery, scaffolds, agriculture, tissue engineering, energy, solar cells, water filtration. So there are many, applications of this particular technique. Now, coming to the wound dressings we are designing, it is basically the gelatin based wound based material. Why we have used gelatin, I want to explain it here. Our skin is basically uh, the main component of our skin is collagen, the collagen protein, and gelatin is basically the degraded form of collagen only. So that is why, since the structure is same with our skin, so that is why we have chosen this particular material. And moreover, this is non immunogenic and biocompatible. So that is why we have selected gelatin for the wound dressing material. Now we want the gelatin in the nanofibers form, but there is a problem with gelatin. Gelatin has a poor mechanical properties. It lose its fiber morphology in the aqueous environment. Whenever we put gelatin, I think you have seen the jellies. The jellies are also basically prepared of gelatin only. So whenever the gelatin comes in the aqueous environment, it actually forms gels. So it lose its fiber morphology. But we want the gelatin to be in the fiber morphology only. Then it is readily degraded by the tissue proteases, and that is why we need some kind of cross linkers which can actually help in maintaining the nanofiber morphology of gelatin. So this is the beginning. We want gelatin in the nanofiber morphology. So this is the problem where we are going to work. So we thought, okay, we will check some cross linkers where we can actually maintain the nanofiber morphology of gelatin. And we came across many cross linkers like glutaraldehyde, glyceraldehyde, genepin, EDCNHS. They're very excellent cross linkers, but the problem with them is they are cytotoxic. Some are cytotoxic, and some takes long duration for basically cross linking. And most of them, they basically use organic solvents or even water they're using. But again, if we cross link gelatin in water, again it will lose its fiber morphology. So we thought, now which cross linker we should use. So then we actually came across a very versatile material called polydopamine. Now when we came across of polydopamine, we were only aware of few facts about it. One thing is, this polymer, it has adhesive properties, means it can bind two structures. It is basically glue like properties. Second thing we came across is it make a beautiful coating on any surface, whether it is a fiber surface, whether it is glass, whether it is ceramic. It makes beautiful coating on any surface. Then we came across that this material, polydopamine, it has antimicrobial properties, and also people have explored it in tissue engineering or cell engineering applications. So we thought, okay, this polymer, it has all the properties which we require. It is antimicrobial, it has tissue engineering properties, it has the capacity to glue, and even in cross linking, the cross linker basically glue the fibers. That is what is the role of the cross linker, to strengthen the fibers. It basically bind the fibers with each other. So we thought, okay, we can try this polymer. Now, I just want to tell that why this polymer is called muscle inspired or bio inspired, because if we see the structure of this, polydopamine, it actually resembles to a protein which is released by the this muscle animals. This is a muscle which basically release this MEFP5 protein, whose structure resembles with polydopamine. And these muscles, they use this protein to bind with the rocky surface due to its gluing nature, and it release this protein and it help in the binding on the rocks even under the water. So that means this protein has a very strong adhesive properties. And since this protein has the structure same as polydopamine, this polydopamine is called as muscle inspired polymer. Okay, so when we were deciding that why not to try polydopamine as a cross linker, we actually came across another paper where basically they use polydopamine to bind polycaprolactone nanofibers. You see here that fibers, they are actually attaching to each other in the presence of polydopamine. So they are binding to each other. So we actually checked this paper and we saw that how they basically did the polydopamine coating on the nanofibers. So we basically saw what they did. They took PCL, polycaprolactone nanofibers. They dip in polydopamine, this 2 milligram per ml of polydopamine in alkaline environment, and finally they see that the nanofibers, they got strengthened. So we thought, okay, we will use the same procedure. We take gelatin, we dip in dopamine solution 2 milligram per ml and at pH 8.5. Let's see what happened. So you see, this happened with gelatin. This is beautiful gelatin nanofibers, which we designed using electrospinning technique. We dip this nanofibers in 2% dopamine solution at pH 8.5, and this is what happened. Whole morphology is completely merged or lost. So basically then we realized polycaprolactone is basically a synthetic polymer. It don't merge while dipping in the dopamine solution, but our polymer gelatin, it is basically it's a gel kind of polymer. It cannot it cannot take this aqueous medium. So we have to come up with some other solution. So we actually checked that what are the other ways we can polymerize this dopamine into polydopamine and cross-link the fibers. We came up with few methods, like some did in air, pH 8.5, oxygen. So there are certain methods reported, but then we came up with a new method. This is our discovery, you can say. This is our patent. Here what we did, we actually realized from the literature that to prepare polydopamine from dopamine, we need only the alkaline environment. So we thought, why not to use ammonium carbonate? So here is the chemistry. Basically, when the ammonium carbonate it break, it actually creates an alkaline environment because of the formation of this carbonate and bicarbonate ions and ammonium hydroxide. So we thought, okay, what we will do, we will basically spin gelatin with dopamine. So both together, we will put in the syringe, we will spin it, and after that, whole fiber material, we will expose to ammonium carbonate, and the dopamine will be converted into polydopamine. And this is what happens.